Planets, in fact, Autostru was right. Planets were found around short period planets, and this year I was so thrilled that Didier Queloz and Michel Mayor were awarded the Nobel Prize for their work on exoplanets. That was amazing. My only wish is that the third one might have gone to Alex Volchin for his discovery of a planet around a neutron star, but maybe next time. Here's their data, right, which were taken with the LED spectrograph. And sorry, the quality of this plot isn't very good. I just pulled it, did a screen grab from their Nature magazine article. So this is 51 Peg B. It had a mass that was almost the mass of Jupiter, at least that's M sin I. And it was indeed in a 4.23 day orbit. Like, planets are not supposed to do that, right? That's what the first thing all of us thought. And you can see that, you can't actually see this very well, but here is the data from September to November of '94. The data are phase folded, which means they found the underlying period and then they folded the data. Look how sparse these data points are. And then clued in to something might be going on. January to February, this is 51 Peg. They observed, they got more data points, right? There's some scatter here, but maybe it's a second planet, who knows? And then in July, 51 Peg comes back up, and they're observing it like mad now. And their Nature magazine article appeared in November of 1995 of this year. So that marked a real turning point. But I would say that, so if you phase fold and stack up the observations from different spectrographs, the California Planet Search team was also looking at the Lick Observatory. And look at the error bars here. So the amplitude is big. It's about 50 meters per second, right? Big. You can hardly miss that. It's like shooting fish in a pond now. But the error bars were about 10 or even 15 meters per second. And I can tell you, as I was a postdoc at the time, and when I asked, could we do better than that? The answer was, Debra, no, you don't understand. Stars, it's not just that you're measuring the velocity of the star in its orbit. The star itself is this boiling cauldron of hot plasma, right? With velocity flows that are hundreds of meters per second. That we can do this well is remarkable. And I had to sort of agree, right? But anyway, you will see the time went on. And in 1995, when this planet was discovered, it hit the cover of Time magazine, not because astronomers found the planet, but because it renewed people's excitement about the possibility of, if there were planets out there, there might be life out there as well. No sooner was 51 Peg B announced than astronomers tried to kill it, right? And so there were a whole number, at least 50% of the astronomical community did not believe that the interpretation of the data was correct, right? They agreed that, wow, this is the most beautiful radial velocity data that we've ever seen, but, sorry folks, after all, a Jupiter in a 4-day orbit, not supposed to happen, right? Why wouldn't the star just completely ionize the, gas and all of it and leave? So David Gray, who is like a god in spectroscopy, right, published a paper in Nature magazine, and I think the initial article title was 51 Peg, A Planet Vanishes, and his idea was that in fact what we were seeing, what astronomers were seeing were line profile variations. So maybe there's some new kind of previously undiscovered non-radial pulsation in the star that had a period of 4 days. That's a really long period, but who knows? The other idea was that maybe we weren't looking at something, we only see the radial velocity component, the projected component along our line of sight. If we were in fact looking at two stars, a binary star system, which was almost, but not exactly, face on, then the projected radial velocity component is about that big. You could make it about 50 meters per second. So that was another explanation. We countered at the time that, but then you would expect to see X-ray variations, right? A whole bunch of other reasons. Still, it wasn't an easy sell to astronomers. And the one thing we said was, look, 1 out of 10, statistically 1 out of 10 of these hot Jupiters is going to transit, right? And when we see a transit, which we predict with our radial velocity measurements, that will tell us the size of the object that we're seeing, and we'll know for sure whether it's a planet So in those early days, you know, starting going back actually to 1989 with HD 114762, something like a 12 Jupiter mass planet, which was interpreted as a maybe possible brown dwarf. 1995, 51 Peg. 96 saw several planets discovered, 47 Uma, 70 Ur, Tau Boo, Ups and, which is one of my favorites. And then in 97, 55 Cancri B, another one of my favorites, which you'll see more about today. I don't know why we discovered that twice, but sorry. So anyway, all of these planets, you know, were press releases, and the documentary crews would swoop in, and it was like a big to-do. But still, a good portion of the astronomical community didn't really do this. So I've been working on this a long time, as you can see. That actually is me a while ago. From looking at Lick Observatory on Mount Hamilton, you can see how the city of San Jose is glowing with an orange color because the astronomers convinced the developers to use low-pressure sodium lamps, and that preserved the quality of the spectroscopic data at the observatory. It was incredibly important. You see two, you know, emission lines of sodium, and the rest of the spectrum is clean. So the sort of state of the art has proceeded in the following way. You can see on the x-axis is time. So 1995 marks the discovery of 51 Peg B. And then over time, you know, for the next few years, we found a number of planets. And this is the velocity semi-amplitude. All of these planets were very much sort of Jupiter mass planets. They're big planets, right? And with time, we got a little smarter, right? We learned how to improve our observing cadence and some of our analysis techniques. And in 2003, the HARP spectrograph was commissioned, right? So gradually you see this trend over time where we're finding smaller and smaller signals. And we can put down, you know, there's what we'd expect for Jupiter, 12 meters per second, Saturn. The Earth is way down here, right? So it's a long, empty gap here between the things that we've been finding with radial velocity measurements and the signal that you would expect for the Earth. So are we stuck there? That's kind of the question. Do these planets exist? That could be another question. Maybe nature doesn't make the planets. Maybe there are some Jupiters, but no small planets. We know, fortunately, because the Kepler mission was launched, that that's not true. So with Kepler, all of these green dots represent the Kepler discoveries. So I just sort of sketched in the radius of Jupiter, the radius of Neptune, the radius of Earth, and the orbital period again here, and then plop down our favorite planet to show you that once again, you know, even with transits, we're not really getting out to discovering temperate rocky worlds. Most of these planets, this is a logarithmic scale, right? So most of these planets have orbital periods of sort of 10 days. It's kind of remarkable that they weren't in the radial velocity discoveries, right? But they're to be alive at this time, you know, to see all this unfold. And so here we are. That's great. Okay, so as I said, we know the planets are there, but we haven't had the sensitivity before to detect them. Here is the planet mass. These are all of the radial velocity detections, and it looks like it's fewer than 700 because many of them are up here at larger masses. These two dashed lines show you the velocity amplitudes of 0.3 meters per second, 30 centimeters per second, right? Still bigger than the Earth, which causes a reflex velocity in the sun of only 10 centimeters per second. But these are things that we might imagine detecting, I think, with Express. And there really are not very many planets that have been found there, right? So it's a wide open field. Earth, again, all by itself. And then here are the Kepler planets. And you have to like look at this and say that there's no way, I mean, I can't imagine, right, that nature put planets like this around the Kepler stars, but not around the stars in our solar neighborhood. So again, I think that they're there, and these planets, I call them the Kepler lost planets, right, are largely missing, right? Look how dense that population is. So here, you know, we're finding the planets, the Jupiters and super above Neptunes, but down here we really undersampled this population. So that led me to come here and give a pitch to the Lowell astronomers maybe 5 years ago to build an instrument called Express. Express is the third instrument that I PI'd, and with each instrument I tried to build a little, test a little, and understand more about what it was going to take to drive our precision. Because over time, if you remember that plot, or if you remember my statement at the very beginning, that with 51 peg, people said, yeah, how can you do better than 10 meters per second on a star that's like this boiling cauldron of plasma, right? But we did start to do better. We got down to 3 meters per second. And then when I would ask, okay, so now what's the fundamental limit? Then the answer was 3 meters per second. Okay, so then we pushed our precision down to 1 meter per second, and we saw now the floor of the stellar noise moved down to 1 meter per second. So I've been driven to ask the question, what do stars look like if your instrumental precision is 20 centimeters per second? What do you guys think? Are we going to see 2-3 meters per second scatter, which is what we see in the Kepler stars? Who knows, right? You have to do the experiment and see. So Express then was designed, as Dave can tell you, one of my more annoying quotes is, there are 100 things that can go wrong, and if we just get 99 of them right, it won't be good enough. So we thought really hard on every count, and one of the major breakthroughs is that we're using a laser frequency cone, which is remarkable. The precision of our instrument is about 140,000. It was designed to be 150,000. We are a little bit shy of that. It's in a vacuum enclosure, has precise temperature control in the room. We used an in-bar optical bench. We use octagonal fibers to collect the light behind the telescope, and then that octagonal fiber runs down to the spectrograph room, which is on the bottom floor, where the light comes out, is split into 2 half-moon shapes and stacked and injected into a rectangular fiber. All of that is going to mix the modes, standing modes that you can get when you put light into a fiber. And then we shake the fibers, because if you were to shine a laser through a fiber and project it onto that wall, you'd see a speckle pattern. And if you move the fiber up and down, you'd see the speckle pattern rotate. But if you move the fiber like chaotically, then the speckle pattern in a 5-minute exposure gets all smushed out, all smoothed out, right? So we do agitation. We have designed an LED flat lamp. Dave was actually a key in this work, which has an inverse spectral response to our spectrograph. So our spectrograph has higher throughput in the red and low in the blue. So our blue LEDs are really powerful and red LEDs less, so that we get something that's kind of flat. The camera design for Express was optimized. Everyone optimizes in Zmax so that all of the different colors of light, after they go through the atmospheric dispersion compensator, will fall on the same spot. But Colby-Jurgensen added another optimization for stability in the line spread function. So this is, as far as I know, the first time this has been done in an instrument. So the camera has been designed to be insensitive to changes in pupil illumination. As we, if the illumination were to move around, the line spread function stays super stable. We did something that was considered to be like sacrilegious. We put in a focus control motor. The motor, of course, is outside of the vacuum chamber, but one of our optical elements in the camera will slide back and forth to maintain a constant full width half max, so we check the focus. At HARPS, which has set the standard for the last decade, they have no control, and Francesco Pepe will tell you, don't put any moving parts inside the spectrograph. That is just the wrong thing to do. So then you look at the HARPS full width, the line spread function, and when they first closed up the vacuum, it was nice and sharp, right? And over time, it's been getting broader, because that's what happens, right? That's entropy. There's mechanical relaxation inside of the spectrograph, and it can only go one way to broaden that. So we have, in our control freak mode, have put it in focus, and I'm not unhappy. I would do it again. We also, we have to correct for the velocity of the Earth. The Earth is moving with 30 kilometers per second speed as it's going around the sun, right? And we're trying to measure the motion of a star to, let's say, 10 centimeters per second. And we're on this moving platform, so we have to correct for that. And it's not, so let's say you take a 10-minute exposure. What time do you use to say, I want the velocity of the Earth at the start time? No. The end time? No. The middle time, that's what I want. That's not good enough either, because cloud coverage can change so that you can get a difference in illumination from the beginning to the end of the exposure. We've known this for a long time. And so we calculate the photon-weighted centroid of our observations and get the ephemeris to correct for the Earth's motion for that time. That wasn't good enough either if we wanted to go down to 10 centimeters per second. Because if we're observing a star through an air mass of 1.5 with a 10-minute exposure, then from the beginning to the end of that exposure, then the differential extinction in the blue relative to the red changes. So we have a little, pick off a little bit of light. One of my students, Ryan Blackman, developed this entire system with help from Dave. Picks off the light inside the spectrograph, samples just 2% of it, sends it to a fiber. Now we have a tiny little, spectrograph, low resolution spectrograph that we bought from Andor or something. And we correct for the barycentric centroid as a function of wavelength too. Okay, so then we also have been worried about the E2B detectors because they lay down these little 1,000 by 512 angstrom chunks with a stepper motor, and so there are stitching errors because every time they go and lay one down, lay one swath down, it's independent of where the other swaths are. We need a big detector, and so we would have had stitching errors with that. Instead, we went with STA. They lay down all of the pixels on their detector with a photolithography process that puts everything down at once. So we avoid that. There are other problems with that detector, but I think we figured out most of the issues. The detector had higher transfer efficiency, and we tried, but probably not successfully. We have some measure of the interferometric measurement of the subpixel sizes, so the pixel non-uniformity in the detector. The idea was to get this for every pixel so that we could actually correct for intra-pixel quantum efficiency variations, right? We haven't gotten to that point yet. We worry a lot about telluric modeling. We're looking through the Earth's atmosphere, which imprints a spectrum in all of our stars. But the Earth's atmosphere is moving with the Earth, and when we imagine looking at stellar lines, those telluric lines will raster back and forth through the spectrum, so we've got to correct for that. And then we have a deployable tertiary that permits very high cadence on the DCT telescope. So when we switch over, like we'll share nights often with other people, right? And the telescope operators roll in the tertiary mirror and we are off and running with the spectrograph. So here's that sort of picture of it. You can see that we have springs on it. One of the first things we did at the DCT was drill a big hole in the floor of the dome. And we poured our own pier so that this is completely vibrationally decoupled from the dome. So I will say this high resolution instrument was really designed, I thought of it as an experiment always. Do we need high resolution? Will high resolution really help us to get the precision, right, that we want? And so this whole spectrograph with such high resolution was really designed to look at bright stars. I would say brighter than sort of, you can look at fainter stars, you just won't get, the sub-meter per second precision on them. And I would say the precision is degraded in a way for fainter stars that we have not yet characterized. So I'm not even trying to look at 10th and 12th magnitude stars because, as you'll see, we can do so much with the bright stars. Okay, so here's a spectrum of 51 Peg, the first classic exoplanet discovered by Mayor and Coulomb. And you can see so much detail. This is such a beautiful spectrum. It goes from below the calcium H and K lines at 390 nanometers, and up here to about maybe 780 nanometers here. You can see sodium D lines, that H alpha line. Let's see, maybe that's a calcium IR triplet. Anyway, lots of lines, right? And so what we're measuring is the shift of these lines as the star moves towards us and away from us. All of these lines span several pixels, like 10 pixels. And we're trying to measure the motion of those lines at the level of about 1/1000th of a pixel. Okay, so those big lines. That turns out to be tens of silicon atoms on the detector, but I don't like to think of it that way. It's too scary. Okay, here's a spectrum of our laser frequency comb. And so to get down to our goal, our target precision of 10 centimeters per second, something that's never been done before, we knew that we were going to have to calibrate, you know? In 2005, the laser frequency comb technology, our idea, was awarded the Nobel Prize, and it has since now been developed to be used as an astrocomb. So we use a pulse laser. The pulse laser is then cascades down through all of these frequencies, producing an emission line at all these points, roughly every 10 pixels in the spectrum. The entire underlying spectrum is locked with GPS units, to 4 GPS units in the sky, with a precision of millimeter per second. So these lines are not moving. We've never had this kind of wavelength calibration before, and I would say it made a big difference. It was also a slight pain. We had a learning curve. Okay, so when we started observing with Express, we took an hour's worth of data with the laser frequency comb, and you can see this is not what we wanted, right? To have the velocities changing by 5 meters per second. Our wavelength calibrator that's supposed to be like rock stable. And it took us a while to figure out what was going on. It was subtle. This turned out to be a beat frequency. We didn't realize that the laser frequency comb was strobing at 60 hertz. And we knew that, and we had vibrations in our detector. And our detector was not using line power 60.000 hertz. Instead, it had its own power source running at 60.0024 hertz or something. That frequency difference is enough so that we ended up with this beat. So now the question is what to do, because of course I have no money, right? And a big problem. And everything I could think of was going to cost $50,000 or be a major change. But fortunately, again, I work with really brilliant people, and Andy Shimkowiak figured out what was going on, and also said, if we could reprogram the card on the laser frequency comb to run at 55 hertz, then the beat is still there, but now the period is less than a second, and we don't care anymore. That's what we did. And then in January, we took data, and this is what we got. So then, again, I was slightly panicked because, okay, the RMS here is 30 centimeters per second. It's a lot better. So I shouldn't be too greedy, but, this is not what we were expecting. And what we discovered is that somewhere in this time, our fibers have become tangled and we're trapped. We have a fiber agitator that's doing this motion that I described before. And one of the fibers had become wedged. And so this is the modal noise now that we would get if we didn't have that agitation. So we pulled the fiber out, we kind of redesigned some things. Here you see, let's see, I think this runs as a movie. Yeah, here we go. That's our fiber. It's kind of comical, right? The fiber agitator, these two arms which are running at different frequencies so that it's quasi-chaotic motion. And that takes out the modal noise so that now we get down to here, 5 centimeter per second when we cross-correlate, a series of laser frequency comb conservations. So that's where we want to be. Now, still this problem, right? My whole life I've been told the floor of the stellar noise is 15, or maybe it's 5, or 3, or 1 meter per second. But, it's going to stop you, and so you're wasting your time by building an instrument that will do 10 or 20 centimeter per second precision. And my whole life, this has been like every night. This keeps me up every night. I think about that. That probably is true. So we have all of these problems. We have the barycentric motion of the Earth. We also have telluric lines in the Earth's atmosphere that are way above and beyond the instrument, control of the instrument. We have changing thickness of the Earth's atmosphere, but that I just mean looking through different air masses. And then we've got, of course, the activity on, this is the sun, right? And you can see the coronal loops, and you can see how it's a boiling cauldron of plasma, hot plasma. How can that possibly average out? Okay, so first I want to show you how we've dealt with, I described how we dealt with the barycentric motion, that we have this second spectrograph that's calibrating for wavelength dependency and calculating the centroid of time. And that gets us down to an error of about 1 centimeter per second. So that's going to contribute our error budget there. This was the next big challenge, the telluric lines, and here I was so lucky to have an undergrad who's just absolutely amazing. This was his senior thesis project, was to do telluric line modeling. So people tried to do this. Sometimes you observe a B star and then you divide by the B star spectrum. B stars are featureless, and so they just record the telluric spectrum of the Earth, and maybe you divide by them and you hope that you saw a B star that was looking through exactly the same column density of air and so forth. And other people have tried building radiative transfer models, which are very complex. They use the high trans coefficients for line formation. And just from first principles, building a building a spectrum of the telluric lines. We took, with Jeff Valente's urging, decided to just put all that aside and do something totally empirical, totally data-driven, right? And Christopher Lee was both a CS, computer science, and astrophysics major. And my big problem with Christopher is that Amazon, Google, and Facebook always want to hire him, and I keep pulling him back. So he's designed, here you can see this 100% empirical linear regression model that he built right here. And in black is this underlying spectrum, which is going to include both the star and the telluric lines. And in blue is his telluric model, right? So it runs on all of our spectra now in seconds, creates a telluric model. Here's another part of the spectrum. The blue is shown as the telluric. When we sent our paper in to be refereed, the referee said, well, but look at, there's this line, how are you going to convince me, there's a line here, how are you going to convince me that this part of the line is really the telluric component and the rest is the stellar line component? And so we said, okay, we have the spectrum of this star taken 3 months later. Now the barycentric velocity has pushed the stellar line away, and the telluric line just sits there exactly as it was modeled originally. So this has turned out to be really powerful. If you use Express, you get all of this stuff for free. You get our optimal extraction, you get the wavelength calibration, you get the telluric model. It just is built into the pipeline. Okay, so now how are we doing? Well, here again are the discovery data for 51 peg, phase folded. Here's the Express data, and you can see that it really kind of just falls like, there are error bars here, they're just smaller than the plot symbols. Okay, but fine, as I said, that's a huge signal. If I can't do that, then I shouldn't be here. Here's a little harder case. This is 55 Cancri, which is known to be a 5-planet system. And so here in Bourrier et al., 2018, using archival data with more than 1,500 data points taken over 20 years, they revisited the 55 Cancri system and fit all of the planets that they could find. And so here is their model. And I showed the Express data. This is, again, 20 years of data, 1,500 data points. This is 14 nights with Express. Okay, and the really interesting one to me, of course, is this guy, because now we're getting down to small amplitudes. And in the case of the archival data, right, it was kind of hard to see this signal. But it really stands out clearly here. So we remodeled the 55 Cancri system. Here is a fit to the data. There are multiple planets. This is what happens, right? You just have one time series of data. And so what you can't see by eye, I mean, I think everybody could probably pick, how many planets can you pick out? Oh, this is a good question. It's a good question. Here's one, right, that period. Then there's also this thing going on, right? And then there's also this thing going on. So kind of by eye, for sure, I see 3 planets. But then I see that this is kind of like not perfectly in phase, so there's probably a 4th planet that's pushing things around. Here are the Express data model now for all of the planets. This is B, C, D is 14 years, so we only get a little swath of that in less than a year. Here's E, right, which is really remarkable. And for those of you who know what the Rostrom-McLaughlin effect is, we're pushing really hard to see if we can measure that in E, because it transits. And then here's F, which is a planet that I published for 55 Cancri in 2007. It has a 260-day orbit. But then when we looked at the residuals, we discovered that actually there might be one more planet there. And this one has a period of about, if I remember, 88 or 90 days. It looks pretty good, but I would still say it's still, there's something there, which I believe. I don't think we've nailed down the period exactly yet. But I think that this is right. So for 20 years, right, this signal has been sitting in the data, and we just pulled it out in the last, with just a few months of observations. So you get some sense of our precision here, some sense maybe of accuracy, but one of the things that we decided to do is look at the Jupiters in very eccentric orbits. And the reason is that when you have a Jupiter that, let's say it's in a 22 or 62-day orbit, right, but it's very eccentric, so here's the star, it comes in here and then it's going out, and the whole time it's precessing around the star. It's dynamically cleaning out the entire solar system of planets, right? Planetary system. So the residuals to an eccentric planet fit would give us some real indication of our on-star precision or accuracy. I don't know quite what to call it. And so here are two systems. HD 3651. is a system I published in 2003 using Lick and Keck observatory data. You can see it took a lot of data points before we were convinced that we had found this 62-day period. Here's the express data. Okay, we had the advantage of knowing that it was there. And also, let's see, right about here, we had, at Yale, we had the partners meeting. And at the partners meeting, everyone was talking about these TOOs, right? TOO observations. And I was like, wow, you know, it would be really cool because I'm not coming back to Lowell until here in the orbit. If we could just get this data point. And so, is Maxime here? I don't know. He kindly gave us like 10 minutes of his time, 20 minutes of his time at the changeover. And in a few hours, we nailed it, plopped it down here. So this is periastron passage. The planet goes through here very quickly and would have been hard to get without that kind of flexibility. So that was great. And here's HD 17156, another eccentric Jupiter in a 22-day orbit. And here's the residuals. So 42 centimeters per second for this guy, which is a K dwarf. And then for this star, which is, I think, a late F-type star, 1 meter per second residuals. And you can compare those to what has been done in the past, where the residuals were more like 4 meters per second. So this is good. Now, this planet also happens to transit, and transit will occur right about here, right? And so we sat on this star on October 31st to see if we could measure the Rostrom-McLaughlin effect. This is straight out of the box. I haven't done anything fancy here. I just laid down the velocity points, and what you see is that the velocities first go up and then go down, right? That's the effect as the planet is blocking out first the approaching limb of the star and then the receding limb of the star. And so that has an amplitude of about 10 meters per second, it looks like to me, but my graduate student, Sam Cabot, who's working with Joe Loma, will do a lot better on this. Okay, so this brings me to the part of the talk. What do stars look like, which are stable stars, right, when you look at them with 20 centimeter per second precision? Okay, so here we go. Here's a star. I just observed this one last night again. It has our internal error bars of about 20 centimeters per second. This star is maybe, I'm going to say it's like 6.5 or some magnitude, something like that. And here's the data over 100 days, right? The RMS scatter is about 68 centimeters per second. So that is far below what I believed, you know, with the 1 meter per second errors. And then what is left behind here? Is this stellar noise from that boiling cauldron of hot plasma? Or are there planets that are embedded in here? I don't know the answer to that, you know, and it's going to take time to build up the signal. We think it'll take about 80 observations before we finally can answer that. Here's another one. Oh, sorry. Let's look carefully at the title. This is Keck data for the star HD 144579. I chose this star because at Keck, this is one of their best behaved stars in the sense of having low RMS scatter. And I then pulled a set of data from this Keck time series data, which was as good as it gets for Keck. And now I will roll this back and show you the express data for the same star. Okay, stars are not supposed to do this. Okay, this is like, our error bars are 6 centimeters per second, and the RMS over 30 days is 4 centimeters per second. I don't even believe this, but I'll tell you, this is really good. This is already really good. Here's another example, 117043, again, 13 centimeter per second precision, instrumental measurement precision, and the RMS over 2 months is 23 centimeters per second. So that's maybe what stars look like, right, when you look at them with very high precision. Here's another one, 70 centimeters per second with 17 centimeter per second errors. So we can just keep flipping through them. Here's one which I showed at the partners meeting. I don't know what's going on here, but it looks kind of pretty here, like there's something underlying signal, but we'll have time will tell. Now let's go back to our favorite star, my nemesis, aka my nemesis, Tau Ceti. Tau Ceti I observed at Lick Observatory, and I thought Tau Ceti, I was convinced that there was some kind of a planetary signal there. It was our poster child for like the quintessential quiet star, the lowest activity, best behaved star. And at Lick Observatory, that meant that the RMS scatter was between 5 and 7 meters per second. Even with HARPS, the HARPS spectrograph, they see, something like a couple meter per second scatter on this. So Didier Collot and I have talked a lot about this star, which annoys us, because we've always assumed it's our poster child for high precision, right? And because it shows a scatter of a meter per second or more, it's been taken as a justification for the idea that, stellar noise prevents high precision. You're wasting your time. Okay, but what's really going on? So I sat on this star on August 25th, right here, and I took an hour's worth of data, and then I forgot about it until my graduate student came to me and said, something is really wrong on August 25th. I don't know what you did, but it's bad. I'll show you what's going on. The star is varying. And I said, with what period? And he said, 5 minutes. And he said, I know what you're going to say. That's the P mode period for the star. And it's true, but the amplitude is too big. So I said, okay, the only way to solve this is to look at another star, which we did, New-Her, and then look at Tau Ceti again. And this is what we ended up seeing. So here was the problem on August 25th, right? That the amplitude is really large for P modes. But we know that P mode oscillations are stochastic, that there's, come in and out of constructive and destructive interference. So maybe this has been going on all the time, but I pull one point here and another point here, and I don't understand why I have this scatter in the data, but now we do. And so in both cases, on August 25th and whatever date this was in October, I think the 8th, we see a 5-minute signal, right? But these, something interesting is going on here. So we're going to understand this noise better. And I'm working now with some people at the Flatiron Institute, David Hogg, Megan Bedell, and my graduate student, Lily Zhao, is there for a semester. And they think that they can actually use the P modes and not just average over them, but actually come up with an underlying model for them. I'll believe it when I see it, but if it's true, then it means that they can remove P mode oscillations in a way that we didn't think we could before. And this worries me because this is much bigger than I ever expected. Okay, so now it would be right to say maybe something's wrong with your velocities that show these super flat ones, although I did show you we get 51 peg right and 55 Cancri right. But we have some stars like Epsilon Eridani, which has an 11-day rotation period. And indeed, we see this spot signal, right? The signal that you get because the spots on the star are on the surface of a rotating star. And the scatter that we get is about 7 meters per second. This one bothered me so much that in 2012, I bought some time on the MOST satellite, and we observed it photometrically from space while we got radial velocities from Chiron at CTIO, and showed that although they were pi over 2 out of phase with each other, that this was definitely spot noise on the surface of the star. Okay, so stars are doing that. Now, if I try, the one thing that I did not appreciate when I started this project 2 years ago, or even 2 months ago that I didn't appreciate, is that these signals that come from the stellar atmospheres at very high precision are obviously incoherent very quickly, right? So we knew that they would lose coherence after a couple stellar rotation periods. They actually, at high precision, lose coherence much more rapidly. Here's another star, HD 101501 61 UMA. also a young spotted star. This is also, something else going on the surface of the star. So we've been modeling what does it take in running simulations to detect low mass planets. We injected a planet. This is actually a real Kepler planet that was discovered, 2 Earth mass planet in a 23.5-day orbit. One of the lost Kepler planets, right? Could we detect this with Express? The first simulation we ran was in all of these cases. This row has 40 observations. This row has 80 observations. So after 40 observations, with an error distribution centered on 80 centimeters per second, so this is typical of Parkes precision, right? You can see that the signal is not popping up here. This is the line marks the real signal. There's some alias or something coming up here, but we're not seeing the real signal. Even after 80 days, right, we're gaining power. And if we look for, 240 days, yes, finally, this power will pop up. And that's how those low mass planets were discovered with Parkes, with 400 radial velocity data points. But with 0.3, 30 centimeters per second, which I think I've shown you now is not our worst case, but, maybe typical case scenario, after 40 observations, this comes up very strong power. We would know right away that we're onto something, right? And we would keep looking at it. And after 80 days, it would get sharper and taller and narrower. Okay, at 10 centimeters per second, which we reach on our brightest stars, the power pops up like incredibly strongly, even after 40 observations. So this is helping to define our project, the number of observations that we need, the signals to noise that we need, the precision that we need. I'm going to just flash through these next 2 plots because there's 3 years of work that's gone into them, working with people in the data science department at Yale. But this is a simulation created by one of my students. It almost takes too long to explain, but here we've injected, we've created with SOAP data, looking at simulated data, injected a spot, also injected baculate, and then a planet. And we've asked whether we could detect this spot. And on the bottom is the resolution. So we're typically using resolution 50,000 at Lick and at Keck Observatory. And we would aim for signal to noise of about 100. So we're down in this corner where we can't really separate out those spot signals. Another way of saying it is that the spots are doing something to the line profile which is different than the center of mass Doppler shift, but that data is binned down. The data are binned down, so that with low resolution you can't really detect them. But in high resolution and high signal to noise, we do better. So I think we're doing better than even these simulations showed us, but this is mostly just to tell you guys that we're not ignoring photospheric noise. We know it's a big problem. We're working hard on it. This is hot off the press. One of the statistics graduate students has developed a new technique using Hermite Gaussian functions to decompose the radial velocity signal. And the bottom line, again, just in a very conceptual way, he put in a 10 into the SOAP data, which is simulated spectrum, a 10 meter per second exoplanet and a 1% equatorial spot. And these represent the p-values, which are uniform in the case of the planet with his method, but which show this very incoherent behavior for spots. I don't know yet, I can see the path, but I can't see the end of the path. I can only see the next few steps. And I can tell that we're on the right path trying to figure this out and finally disentangle the photospheric noise. When that happens, then that periodogram power is going to grow much more quickly, right? It will require less observations. So then maybe I can go from, I think I can safely say we'll discover 40 planets with Express in the next few years. Maybe we'll finally get to the 100 Earths that I hope to finally detect. So I want to just stop there and thank everybody, especially including the whole Lowell Observatory team. Such an amazing first-class team to be able to work with. I feel so lucky to be able to do that. And all of my team, who is, again, they're just absolutely geniuses. And I wanted to quickly now show you, if I can get over here, Okay, this is the interface if you want to use Express. So this is you just pull up a Safari window, you load up express.lowell.edu, and this comes up. So here, down here, let's see, yeah, here we go. Here's my target list that we'll look at for tonight. So here I've clicked on the BON, beginning of night calibrations, and this window comes up. And so here I can, if we're connected to the internet, I can start a thorium argon exposure. Uh-oh. I see what's happening. I may not be connected to the VPN. Anyway, I was going to show you how easy it is instead I showed you it. Anyway, but it is quite a beautiful interface. Has so much information. So if you are observing, there's a window that shows you as the counts come in from Ryan Blackman's exposure meter. Shows you the counts. We can terminate the exposure when we get the right signal to noise. Okay. Now you're doing something. Okay, so now it will start the exposure. All right, so now it's actually taking an exposure, so I'm observing remotely. I've actually done this on the Amtrak train from Washington, D.C. to Yale. And if you're observing, there are a whole bunch of tools here. Like you can scroll to the bottom and you can get information about the weather. You can get the directions, the observing guide to tell you sort of a checklist, essentially.
Exposure complete.
There we go. That will tell you everything you need to know about operating the instrument. And we can also scroll up here. Yeah, okay. We can also bring up, look at the log sheet that was just created. Okay, good. So I'll go to the bottom of this, because this is the one I just took. These are my observations from last night. Okay, just finished reading out that thorium argon observation. Now we can just look at it, and hopefully we see a thorium argon spectrum there. Okay. Yay, we do. Okay, so there it is. You can see what our looks like. So it's just as that easy to use, and the pipeline also will deliver wavelength calibrated, optimally extracted spectra with Telluric models on them. So I'll end there. Thank you guys for your patience. Questions? Yes.
Debra, your talk is titled 100 Earths. You said maybe it's 40.
Yeah.
I don't care, but could you briefly say where does that number come from?
Where did 100 come from?
Or 40, I don't care.
Okay, 100 came from trying to be inspirational,
okay.
Right? 40 came from being realistic as I was writing the NSF proposal and realized that given the amount of time that I hope to get with the DCT and the signal to noise, it actually requires higher signal to noise than I ever anticipated, but it's worth it because we can drive down to 10 centimeters per second precision, which is what we need. That, you know, when you take that amount of time divided by the time we need, given the brightness distribution of our stars, we can observe about 45 stars, right? Something like that. Now, this estimate does not include the idea that we may reduce the photospheric noise by 30%, which will cut our exposure. Yeah, these are the same stars that I've been looking at for 20 years, first at Lick Observatory and then at Keck Observatory. And these are, in many cases, except for some special cases, we of course wanted to benchmark Express against known planets. But the rest of them are all stars where we have this huge velocity time baseline. We know everything about the star. We know about its activity, and we know its chemical composition. And we know that no planets were found there. But we know from Kepler that they have to be there. It's just that our error bars couldn't detect them before. So we're zooming in on those stars. Yeah, we have a lot of prior information that went into picking them. And then, so we use that to cull down to 200 stars. And then from there, we choose, you know, the best stars. We have a weighting scheme. Brightness matters a lot, but other factors like stellar age and yeah, awesome.
Is there any limitation on spectral time?
Yeah, So I just strongly dislike F-type stars. F-type stars have F-ness, I don't know what that means exactly, we just always say that. I just know that the velocities are all over the map, incoherent, just wildly varying velocities. So I don't even want to go there. So I'm looking at solar type stars, a slight prejudice, right? And then I'd love to go down to the M dwarfs, but EXPRESS is an optical instrument, and the M dwarfs are really faint, and at the resolution. If this were a 10-meter telescope, it would be a different story, right? But for what we have, we've chosen the sweet spot for where we can squeeze out the most science in a new parameter space of exoplanets. Yeah.
You may have mentioned this, but what's the sun's RMS scatter or RV scatter once you remove the planets?
That is a great question. Somebody will be able to tell us.
Jack?
Find out.
But we haven't done the experiment, right? And so Joe is building a solar telescope, as you know, to see if we can detect Venus and Earth. Great, because we have the answer in the back of the book. And we know from HARPS that the floor of the stellar noise is about 30 to 50 centimeters per second. But that's HARPS, right? So HARPS is like still last decade, but we're not going to blow that away. We'll see. Yes.
Maybe related, can you do, I think, gong type observations of other stars and get some idea of their interior structure?
Yeah. So the Tau SETI data actually do that, right? The very high cadence sampling that showed the P-mode oscillations reveal that. So we're actually planning to have a night looking at Tau SETI the whole night to look so that we can get the P-mode, the spacing, new spacing, and the P-mode distribution better than has ever been done before. Yeah. And it's a third magnitude star, so it's easy to do it with super high cadence, yeah. Okay.
This may be an unrelated question, but would this allow you to detect, let's say, Galilean-sized moons?
Ah, good question. It turns out that as those Galilean-sized moons are orbiting in what are the orbital periods? Relatively short periods, that what our technique really sees is a center of mass of the planet and any moons, right? So it's a smeared out, kind of like a ring or a spear-like center of mass. So I don't think that radial velocities are going to get you down to detecting moons. Those probably will have to come with precision transit observations, which show a blip on the side of the transit. Yeah, it'd be fun to do that. Good question, yeah. Great questions. Okay, well, I guess I will be here if you guys have any other questions, and thank you very much. I know. Of course. They do have those physics, and then there's down to yeah, all the science they have to exactly that.
I just want to chat to her.